Welcome. We're now going to have a look at the DC motor. The last lesson was about the torque on a coil, and the DC motor is simply a practical application of the torque on that coil. So having a look at the parts of the DC motor, they're divided into two sections. And the first one is the stator, or stator, and that is the stationary part. And the other part is the rotor, and that's the rotating part. So having a look at our diagram over here, the most obvious part that is stator are the big stator magnets. So these are, I'll just write them, the stator magnets. And these, at the moment in the diagram, are permanent magnets, but they can also be supplied by an electromagnet if we choose so. You can have the electromagnet in series with the DC power supply down here, or we can have it after it goes through the loop. We call these shunt and series motors. It's unimportant, it's not part of our course to know that part. Right, now, the other part that is obviously stator is the power supply down here, and the part that is rotating is the loop, the coil itself. So here is the coil there, and this part here will also rotate, and that is the, we're going to find out, it's called the split ring commutator, and it is a fabulous piece of engineering. Its design is to get electricity into this loop without wires tangling, and also at the same time keeping the torque in the right direction. The stator is, as we'll see in a few moments, is made up of a brush. Now that brush doesn't move, so it is technically part of the stator. And the parts of the coil doesn't exist just as a single loop like this. It would be wrapped around, most likely, a soft iron core, and that would be called an armature. Right, so what is this commutator? The thing that I've been saying is fabulous and a really great feat of engineering. Well, we know from looking at our torque that if the coil goes for the horizontal where the torque is maximum, so here's our torque, there's the north and the south bar magnets, we know that torque is maximum in the horizontal. And as it starts to turn, the torque gets less and less until it becomes zero up the top. If there is zero torque at the top, that means there is no turning moment at that point. There is no turning effect, and therefore the coil will get to that position and just stop turning. Also, at this moment here, because the forces, that's the forces, this is the Lorentz force, this is the motor effect. The forces will be pulling in opposite directions like that, and all it will do will be stretch the coil up and stop it from turning even further. So what does the commutator do? The commutator changes the direction of the current in the coil when it reaches the upright position, the point where it's at right angles to the magnetic field. Normally we draw our motors north and south, where the north and south, the magnets are in the horizontal position and the coil will go there, but you might see diagrams where the north and south are in the vertical. So we'll just assume that it's horizontal in this case and vertical in others. So what I mean by that is our position of the magnets should be in the horizontal here for our discussion. Now, what does this mean? It means it changes the direction of the force on the coil every half turn. So here is a diagram of our commutator. Our commutator is made up of two parts. Its official name is the split ring commutator. It's a split ring because it's made up of a split ring. And it has two parts to it. It's the split ring itself, and these out here are called the brushes. The brushes just form an electrical contact with the metal cylinder here. So the commutator is made of metal, and its two basically big C's like that, big letter C's, and current comes in one way and out through the other brush. Okay, so current comes in, it then goes into this, whatever contact of the commutator it is, and it would go out up through that part of the coil, and the coil would be attached to one and only one side of the commutator, and then the out would also be attached to one side of the commutator. Okay. So here we are, a sideways looking here. So here are the brushes, here's a split ring, and both of these, there's a split ring there, are attached to one end of the coil. Okay, so both of those are attached to the coil, so the coil is up here. Okay, it is a metal ring, okay, and the brushes remain in contact and they slide along the surface of the ring. Okay, the two halves of the split ring are connected to each of the end of the coil, as I just said there, and they are separated. Normally we put a separation, like a piece of plastic or something in there, which is an insulator that does not conduct. So it just makes it easier to keep these sections apart. Right, now how does it work in detail? Always current comes in from a DC. Now remember, we're talking about a DC motor here, so the direct current. So current comes in one way from the battery or from the power source. So we're always going to say it's in through this brush and out through that brush. And here is the commutator A, and that section there is attached to that part of the coil. So current in this coil flows from A to B. So it goes in this direction. So current flows in, up, around there, and then out through that contact through B. Okay? Remind ourselves that the brushes do not move, so the contact is always in through the brush on this side and out through the brush on that side. Right, here it is beginning to turn. The reason why the coil is turning, obviously there is current in this coil and a torque is making it start to turn. So let's have a look at the direction. Current is flowing in. Remember, it always comes in on this side. It flows up there. So it is still moving from A through to B and then out that way. So we're still A to B. We are just approaching the vertical here. At the vertical, we will get the gaps, two gaps, making contact with the brushes. And at that moment, no current will flow through the coil. However, the coil has some momentum and it will continue to turn, just enough for the next part. As it continues to turn over its vertical, the split ring has now made contact with different brushes. So here, I'll just get something. So we've got brush B, here is brush B now, is now making contact with the in brush. So having a look, current still comes in through this side, but it's going to go in through the B side and then make its way around and then out through the A side. Okay? So current is now flowing from B to A. Okay? So what it's done is the current goes in always through one side and out through the other side of the commutator, of the brushes. But it's the different sides of the commutator which make contact with each brush. And so in this case, current flows in through this coil and out through, this side and out through that side. Okay? When it turns through 90 degrees, it will, through 180 degrees, it will be in contact with the other commutator. Okay? So what does it do? It reverses the current in the coil every half turn. So for one half turn, current is in one direction. If current is in one direction, so say current is going this direction and B is that way, then you'll get a force in one direction, okay, using our FBI rules. I'll just wipe those all out, okay, because I don't want you to get confused over there. So while we have B and F in one direction, here is this is side on to the coil, this is the coil side on. That wire there has a force pushing up, force pushing up. The force does not change. However, when it gets to here, the current is going to change and in direction, and then the force on the wire goes in the opposite direction because the current is changed. So using your FBI, your three-finger rule, the I is the one that will change. If I goes from being that direction to that direction, the force will just reverse its direction. So it goes, you're pushing the coil this direction until you get to the top of the coil, top of the turn, and then it'll be pushed in that direction. Now, do not look at any of the formulas here. They are from a different course, and all these angles here. Do not look at them. The reason why we're having a look at this diagram here is to see what we call a radial field. We want to increase torque, and torque equals NBIA sine theta. The more that theta is approximately equal to 90 degrees, the longer this torque is at maximum. Now, when we have our magnets having flat edges like the north and the south and having a constant magnetic field between it, we get a change, an angle between the coil to become 0 at the top and maximum here. So the angle changes and the angle goes from 0 to 90 degrees as it turns around. But if we can make it stay at 90 degrees for longer, we will get torque at maximum for longer. So what we do here is, rather than using straight edges, we're going to use a curved surface. If we use a curved surface, the shape of the magnetic field becomes, it always leaves the surface at 90 degrees, it's directed in, and the returns at 90 degrees. So here, it will go from there at 90 degrees from the surface in and out. So we're no longer getting a constant magnetic field, I shouldn't touch, but we are getting a concentration into the center of the coil. And as a result, this makes the angle between the wire of each of these here and here remain at 90 degrees for longer. And as a result, we get a more efficient motion. Okay? Right. I'm going to stop the video here, and then we're going to have a look at a applet for a motor. So please click to the next video straight away now, please.